school doesn't break. I make it for my TAs. Thank you very much. Well, right, everybody, please shut your laptops, get your name tags out. I know that falls here when my classroom's empty. I can literally track the sun based on the attendance in my classroom. So it keeps tapering. And then at some point, daylight savings kicks in. And so the clock moves back, and then everybody's waking up earlier. Then for a brief while, I have a few more students in class. And then it goes back to normal. Then in the final lecture, I'm basically talking to myself. That said, can you shut your laptops? And folks? I'm downloading the slides, is it? So the reason I want to start this early is highlighted on my sliding. We're going to have to terminate this class a bit early because the next slot has an exam. And they've requested me to, make sure that we're out of here in time because the students will begin coming in early just because they are going to be tense, right? And this means that I will not be able to cover everything in my slides. That's just a handy excuse. I have never been able to cover everything on my slides in this last lecture for this series. And this time around, I actually have a valid reason to say that I won't be able to do it. So we're going to have an extra lecture at 8 p.m. over Zoom today. Just to close out. This is the last of the series of lectures on training the model. And this is probably the most fun one, which means that, of course, this was the one where nobody turned up. And so the rest of you who are here, you're going to get to answer all the questions, right? Let me begin. Here's where we were. We found, by the way, Raghav, did we get the token business sorted? We'll have to do it next class. Right. So we train a network by minimizing a loss function, which is the average of the losses or the divergences for individual training instances. And this is only an approximation to the true risk, which is the expected divergence between the function we want to estimate and the function the network is currently modeling. We minimize this through variance of gradient descent, where we take iterative updates against a gradient or some smooth variant of the gradient of the loss function with respect to the parameters. We also saw that batch updates must process the entire training data before each update. This is the theoretically correct way of doing things, but then it's very expensive. So we prefer to perform incremental updates where we update the parameters after every few instances. So these are techniques like stochastic gradient descent and mini batch update. These are faster to converge, but they may have a greater variance in the results. And this can result in worse estimates. We also saw that trend algorithms like momentum and Nesterow's method tend to smooth out the variations in incremental updates by considering long-term trends and gradients. This can lead to faster and better convergence. And we saw an extension of this was to actually have the learning rate itself also be adaptive based on based on the second order trends in the gradients. And that could lead to better convergence. So moving on, we're going to look at some tricks of the trade. We went through a bit on generalization and such like, right? So here it is again. The loss function is an average of the divergences for the individual training instances, which means that how fast the optimization actually gets to the solution you want is going to depend on this function, the divergence function. And ideally, this must have a shape that results in a significant gradient in the right direction outside the optimum. So if you're not at the optimum, it must be of a form that actually guides you to the optimum fastest, and yet carefully, right? So let's say I have these three kinds of loss functions. Obviously, the one to the extreme left, which is all jagged, is a completely horrible loss function. At no point do you have any indication of which way to go. Although if you take a meta look and go out and look at it from a bigger picture, there does seem to be a minimum towards the left. But at the scale at which you're going to be looking at it when you're actually performing optimization, there is going to be no trend apparent. The one in the middle and the one in the extreme right, they are both loss functions with a unique minimum, and they are both smooth. But which of these do you think would be the better one? Why? So here's what would happen, right? Your steps are dependent on the derivative. The larger the derivative, the greater the steps. So in the first case, the one in the middle, the function is flat, far away from the minimum, and your steps are going to be very small. You're going to take a long time getting to the optimum. And then when you get to the optimum, because the derivative is so large, you're going to take very large steps, almost certainly overshoot, and possibly even bounce out. So this is not a great one for convergence. What you really want is like the function on the right, where when you're far away, the slope is large. It leads you to take large steps. But then when you get close to the optimum, the slope is smaller. And so you take smaller and more careful steps that take you to the optimum. So now let's take a look at a couple of loss functions. And something surprising emerges, right? Here's how we have the let's chalk here. So we can perform one of two tasks with neural networks. One is regression, the other is classification, right? So when I'm performing regression, in each case, you have the output neurons, and the output neurons are going to, you may have one or more output neurons. They get a weighted sum of the outputs of the penultimate layer. And the first thing that happens is that you compute an affine value. That gives you a z, right? So this is within one layer. And then these guys are going to go through an activation, which can be a vector activation or a scalar activation, as the case may be. And this is your final output. Now, if you're performing regression, where you're trying to predict a continuous valued function, what would that activation be? Pardon me?
Single value.
A single value. It's just going to be you would have a linear, pass-through function, right? You're not trying to perform a nonlinear transformation at that point. Typically, you just perform a weighted sum of everything you've seen. So at this point, this activation function is simply going to be y equals z for regression. And for regression, what loss function would you use typically? You're predicting real valued functions. Yes, Katrina?
L2,
the L2 loss, right? You're going to have the desired outputs, and the loss is simply going to be that's your L2 loss, right? Now, on the other hand, if I'm performing classification, you still have the same situation. You compute first you compute an affine function of the outputs of the previous layer. And so that's going to give you a z, right? And this z is now put through an activation function. And what kind of activation function do we typically use for classification? Can you say it aloud? Softmax, right? Softmax or a logistic function. So this entire thing is your activation, is your output layer. You're using a softmax, and this is going to give you a y. You have a d, and we can have some loss function over here. Now, what prevents us from using, and what was the loss function we said we normally used in classification? Cross entropy, the Kullback-Leibler divergence, which becomes the cross entropy if you're using a one-hot D, right? Now, and so we use the KL divergence, but do we need to use a KL divergence? We could have done an L2 over here. What stops you from doing an L2? Nothing really, right? So why KL and why not L2 when you're performing classification? So take a look. We said that we want the ideal loss function to have a bowl shape. There's a reason for wanting to have a bowl shape. So if I gave you the choice of this loss function versus this loss function, which would you choose? Left or right? Why the right? In the right one, the derivative is basically becoming all negligible near the, sorry. So in the right one, the derivative is becoming negligible near the optimum. You're going to take forever to converge, right? So if I were choosing this, I'm going to be taking something steps like this. Get here. Here I'm going to be doing that, and then these things become really small. So which is why we take the L2 and not the L4, right? I'm not taking the fourth power of the error. I'm taking the second power of the error that when I'm performing regression. Because when I take the fourth power of the error, what does the function look like? It's going to be very steep and very flat. So, this is L2. But if I took L4, this would be L4. And yet, when I'm performing my classification out here, for whatever reason, I'm saying that in this case, both cases, I'm assuming that the ideal the target output is 0.5 rather than 0 or 1, just to give you a nice symmetric picture, right? I'm claiming that KL is better than L2 for classification. But the other picture tells me that is not the case, right? So why would that be? For this, we have to consider the fact that, where did I leave my chalk? We have to consider the fact that the softmax is e raised to z over 1 plus e raised to z, or summation, right? This is the format it has. And so now, here's what happens. I can define my function as a loss, my loss either as a function of y or as a function of z, right? And so here are the pictures that turn out. For the classification task, when I define my loss as a function of z, what goes in before the softmax? You get the blue curve if I'm using the KL divergence. Whereas if I'm defining it as a function of z, the L2 is a function of z. When I'm using a softmax activation, you get the blue curve at the bottom. Which of these is the nicer one? Which of these is the nicer one, guys? Somebody say, speak it aloud. The second one, right? So you guys at the back, are you awake? Okay, so which of these is the nicer one? Can I have your name tags? All of you. I need to go and invoke you by name, right? I need to make sure that I know who you are. So as you can see, as a function of z, the KL divergence is actually a much nicer loss function. Although as a function of y, L2 seems to be the nicer loss function. So what is the lesson over here? That we cannot be looking at local characteristics of the loss function. There's something that happens between the variable that you're trying to optimize it with respect against and the final output of the network. In this case, it's just a softmax. So if I go back and just think of, if I had a simple logistic function with a couple of weights, if I plotted the L2 divergence as a L2 divergence as a function of the weights of a logistic function, it actually ends up looking like a flower, which we said was the worst possible thing we can have. Whereas the KL divergence has a bowl shape with a global optimum at the minimum. So which is why we use the KL divergence. But is that enough? Given a choice between L2 and KL, so here's what your network is. Your network has your final output activation, sigma. Then you have the Z's, then you have the previous layer, then you have the previous layer, then you have the previous layer, right? And what the L2 divergence is convex with respect to this guy. The KL divergence is convex with respect to this guy. There's no saying how these things are going to change as you go further down the network. Ideally, you want it convex with respect to everything, right? And so, or at least to the bottommost thing. But given a choice, the KL at least allows us to go one step further down into the network and still have a convex function, which is why I use the cross entropy loss. Does that make sense to everybody? Right, you guys at the back? Okay. So anyway, so now one of the outcomes of this is that if you actually look at this function over here, you will find that the L2 divergence, in the case of the L2 divergence, the derivative with respect to the output of the network was just the error. It turns out that when you're using the KL divergence, the derivative with respect to the affine term, Z, at the output layer just ends up being the error, just because, as you can see, now it begins looking almost quadratic with respect to Z, right? And so in both cases, the derivative with respect to the affine term at the output layer is just the error between Y, the output of the network, and the desired output, which is why the backpropagation algorithm is called the error backpropagation. You're literally backpropagating the error, right? Everyone with me? Okay. Cool. It was very quick. Okay. The answer, guys. First one. What's the answer? Which of the losses is convex with respect to the weights of the final softmax? Someone on Zoom?
KL
KL, right? Because KL is convex with respect to Z, and Z is linearly a linear function of the weights, right? So the KL divergence is going to be convex with respect to the weights of the final layer, whereas the L2 divergence is not going to be convex with respect to the weights of the final layer. That was the point of the split, right? And then secondly, the gradient with respect to the final affine value Z, what was it? Error, which is? Can you tell me which one it is? Y minus D, thank you, right? Okay, so far so good. Questions, anybody? Okay, this was the easy bit. So the story so far, gradient descent can be sped up by incremental updates and can be improved using smooth updates. The choice of divergence affects both the learned network and the results, because the wrong divergence is going to actually end up being very slow to converge possibly, and even taking you to the wrong place. Now, the big topic for the day is batch norm. All of you have dealt with batch normalization in your homework, right? You've read the handout. Did it make sense to you? If you claim it made sense to you, I claim that it didn't, right? There was a lot of complicated math. Wasn't very clear where it came from. And why are we doing this? So for the why, here's the thing. When you're performing training, your training assumes that the training data in all the mini batches are similarly distributed. That was the point of the random sampling, right? You took a mini batch, and the mini batch had a bunch of samples, and you expect the distribution of the mini batch to roughly be the same as the distribution of the training data. Otherwise, you don't. This whole thing is really not going to work too well. It's going to bounce around, right? But are the mini batches going to be identical? What will happen is that your mini batches are all going to be very different. And particularly because your deep network is a nonlinear transform, which shifts the things around in space, even with two mini batches which are very close in the input, by the time they get to the fourth layer of your network, they can end up being very far apart. And so now this means that your actual mini batches may not look like this at all. They end up looking like this. But our optimization assumes this, right? Otherwise, you couldn't really be using mini batch descent. Our notion is that the variance is somewhat small, which means that across mini batches, the loss is more or less the same. And the fact that your neural network is a nonlinear transform, which just moves things around wildly, means that small differences in your mini batches can be greatly magnified by just a few layers of the network, and then all of your mini batches end up very far apart, which violates the basic notion that we began with when we were performing mini batch descent, right? So how can we fix this? The way we want to fix it is we want to move all the mini batches so that they lie on top of one another. But where? Where in space do these mini batches lie? For this, to determine this, we're going to actually learn this location in space, where each mini batch lies. And the way we will do it is that each mini batch is first going to be sent out to origin. Push them to the center. So they all have zero mean and unit variance. So it accounts for the spread, and it accounts for the position. So this, you sort of standardized all of the mini batches, right? And then this entire collection is going to be sent out to the right location in space. You can't learn this shift for every single mini batch individually. What you can do is push them all to origin, and you can learn a common shift to this new location in space. Making sense to everybody? So, yeah. So how would you do it? Add something, exactly, and scale it a bit, right? Because you normalized everything to be unit variance, you scale it a bit to get it back to some more standardized variance, right? It's perfectly. So, okay. Yes. The problem is that you can't really just figure out where they are in space when you go through a few layers of the network. The network moves things around. So your strata in one layer will be completely different in the very next layer, right? So, okay, answer? Yes. Many batches, right? So now, where are we going to perform this mini batch normalization? Now remember that you can do it in different locations. But remember that within each neuron, there's a two-step process. First, you compute the affine term, and then you put the affine term through an activation, right? Typically, we're going to be doing this in that spot there, between the affine term and the activation. So right here, for those who are on Zoom, we are going to be performing the mini batch, batch normalization between when you add up all the, between when you compute the weighted sum of the terms in the previous layer and when you actually apply the activation to this affine term. So we're going to be doing it to Z. Okay. And so what is the operation we perform? Now, within any individual neuron, what is happening is this. You have a bunch of inputs. You compute a weighted sum of the inputs. You may have a bias, but the bias becomes irrelevant because you're going to be subtracting things out. So typically when you use batch norm, using a bias is a pointless thing to do because when you shift everything to the origin in the first step, the bias is going to be eliminated, right? So you will not have a bias. And so then the first step was to move mini batches to the center, right? So the act of moving mini batches to the center and normalizing it means that every single instance in the mini batch is going to be moved such that the mean of the mini batch is 0. Every single instance in the mini batch is going to be scaled such that the variance of the mini batch is unity, right? And so this is for a single instance. This Z is going to be normalized. First, you need to compute the mean of the mini batch. This picture is only showing you a single instance, okay? One instance in the mini batch. But you're going to first compute the mean of the entire mini batch, and then you will also compute the variance of the entire mini batch. Then to normalize the instance, you're going to subtract the mean and divide by the standard deviation of the variance, or by the square root of the variance, which is the standard deviation of the mini batch. Now there's a square root of the variance plus epsilon. That's just to prevent division by 0. Okay? And then once you have done so, what this does is that it sort of moves all the instances in the mini batch into a cluster of unit variance centered at 0. Then the next step is to move it to a new location and a new size, right? So what you will do is to first scale it to the new size and then move the scaled version to the new position. And so that's going to be this guy here. This U, which is now normalized, is going to be scaled up by gamma to the new variance. The new variance will be gamma squared, right? And then you add this shift term beta to move it to the new position. Is that making sense? Right? And now all of the mini batches are standardized. You can expect the derivatives to work and the gradient descent operation to work as you normally do for mini batch descent. So does that make sense to everybody? What we are doing with batch now? Over here, yes.
How do you know what
We're going to learn it for every single neuron, right? And so here's the picture. Within batch normalization, there's a two-step process. The first step is to normalize the U's so that they have 0 mean unit variance. The second step is to scale them and shift them to the new position. So the box on top has two components, the normalization and scaling and shift. And scaling and shift is simply multiplying by gamma and adding a beta, right? So I can just read right like the figure at the bottom. Yeah.
Question on Zoom asking why do we need gamma and beta?
So again, we're trying to get them back. You can just keep them in the same position, but then you're really losing the distinction between, you're losing a lot of distinctions. So the fact of the matter is you can try different things. You're giving us more, it gives us more parameters. We are assuming that each neuron has its own position in space. Otherwise, there's going to be no statistical difference between what happens at one neuron and what happens at the other neuron. That's about it. Now, in practice, I assume that if you got rid of it, you can expect these to be subsumed by later parameters, but it may not happen. So now this business of normalization makes things painful when you're performing backprop. That's where all of those crazy equations that you saw in your handout come from. And why is that so? That's because in your standard derivative computation, your loss was the average of the divergences for the individual instances in the mini batch. but each instance was independently processed, right? So this means whatever output you got for one instance did not depend on the other instances in the mini batch. So this means that when I take the derivative of the loss for the mini batch with respect to any parameter, I can simply compute the derivative of the losses for the individual training instances independently without considering the others, and then I can average those. So that's what backprop did, right? Each instance was individually differentiated, and then you just average them. What happens when you perform batch normalization? Is each term independent of every other, is each input independent of every other input? Why not? Because you're normalizing by the mean and the variance of the entire batch, right? So can I just do this for computing the derivative? Compute the derivative for each one independently and average. Would I be able to do that? Yes or no? So you guys at the back, somebody has to reply aloud, okay? So that's because the divergence now is a function of not just the current input, but also the batch mean and the batch variance. And the batch mean and the batch variance are dependent on the rest of the instances in the mini batch, right? And so training instances within the mini batch are no longer independent. How does that work? If I consider the entire mini batch as just a collection of vectors, right, then the mini batch over here is going to be, this is for the entire mini batch. When I'm performing batch normalization, I have the entire batch of z's, because that's where I'm applying the batch norm. And the output is the normalized and shifted batch of z's for the entire mini batch, right? But the fact of the matter is that, what happened? If I modify this one z1, which z hats get modified? All of them. If I modify any given z, all of the z hats get modified, right? The actual picture looks like this when I'm looking at the computation. So I have all of the z's come in. All of the z's contribute to computing the mean. All of the z's and the mean contribute to computing the variance. Then for any individual, the centering and normalization of each z, I'm going to use the z value itself, but I'm also going to be using the mean and the variance, because I subtract the mean and divide by the standard deviation. And then only after I have done this do I actually apply the activation and compute the output of the layout, right? So I have this extra process, and that block in the middle, that's a change, because now you have interactions. Now, when I'm performing backpropagation, I can perform backpropagation down into each line individually until this point, because they do not, beyond the use, each line is independently processed, and so they are not intersecting with one another, right? So at that point, I can just say that, here was an individual instance. I had a z. Then I normalized it by subtracting the mean and dividing by the standard deviation. And then I applied a z hat, right? Now over here, wait. After normalizing it, I scaled it and shifted it, and then I applied the activation. So now the scaling and shift terms, the gamma and the beta, they are also parameters to be learned, right? So just for reference, I can write this down. That is I have the z command. This is my normalization, which shifts the entire mini batch to have 0 mean and unit variance. So this becomes a u. Then this is z hat equals gamma u plus beta. This is a scalar operation. And then this is put through an activation function, and then you get a y, right? So when I'm performing backpropagation, the backpropagation is going to give me d loss over dy for that instance, right? Then if I go from here to here, let me call this z hat. What is the next thing I would compute when I'm performing backpropagation? Guys? D loss over dz hat, which is d loss over dy times f prime of z hat. So far so good, correct? Now, I have to go back here, but in the process, I also have to compute, because gamma and beta are learnable parameters, right? So what are the derivatives I need to compute going back? I need to compute the derivative with respect to gamma, because this must be a learnable, this is a learnable parameter. I need to compute the derivative with respect to beta. That is also a learnable parameter. And then I'm going all the way back, right? I need to compute the derivative with respect to u. Right? Everybody with me? And what is the derivative with respect? So now I already have the derivative with respect to z hat. What is the derivative with respect to gamma? What is this? Rohan. Okay, guys, I'm calling you by name. Now you're going to have to answer me, right? What is the answer? What is the derivative of the loss with respect to gamma? Go out, wash your face, come back, wake up, be here. Somebody else want to remember the answer? Muiwa? What is the derivative of the loss with respect to gamma?
Is it dl dy times dy d gamma?
So it's dl dy d gamma. You haven't been paying attention, have you? I've already gone way back, right? So use everything that I've discussed. Yes.
dl by dz and ui.
So it's dl over dz hat, right?
dz, yeah.
Z hat over gamma, which is dl over dz hat. So I've computed the derivative with respect to gamma, right? So Heiji, what is the derivative with respect to beta? dl over d beta equals dl over d z hat, because that's it, right? It's an additive constant. And what is the derivative with respect to u, Sunhee? Times now. So we have managed to move our stuff all the way back to, we've got this derivative. We've got the derivative with respect to gamma and beta, which are parameters to be learned. And then we have got our derivative with respect to beta. But here's the point. Now for the rest of it, you guys are going to solve it for me, because we have the time. Okay? Okay? Anybody want to answer? Someone on Zoom, what is the answer to the first question?
First point.
First point. And what about the second one?
It did not come in the poll actually.
Second one too.
Okay. So in the batch norm, the normalized value for ui depends on the zi's, right? Because the z's became u's. So every u depends on every z, but then it doesn't really depend on the u's directly, right? And what about the second point question? Can I think of the batch norm as a vector operation which operates over the vector of inputs? Yes or no? Yes, right? The batch norm is actually a vector operation. And so that's also true. So now I have derivatives all the way with respect to u. Okay, and here is my eraser.
It's there on the left, there at the end.
Okay, let's now, guys, we're actually going to work out the batch norm arithmetic all on our own without looking at slides or papers. So I need a series of volunteers, and if you will not volunteer, then I will volunteer you, right? So we're going to start from the back. And so I can't see your name tags. You're Laura? Okay. So Laura, you are it, right, for the first one. And what's your name? Pardon me? Mingwei. Okay, Laura and Mingwei are going to answer the first two questions, right? So look at this. I have Z1, Z2, Z3, and so on. And then I have U1, U2, U3, and so on, right? Now, I have each Z1 directly influencing the corresponding U, each Z2 directly corresponding, and then all of them influence the mean, which influences all of these guys. All of them also influence the variance, right? And which also influences these guys, right? And then do all of these influence the loss, Laura? Yeah. Okay, so all of these influence the loss, okay? So Laura, what would be a generic term in terms of derivatives? Let's not think about how the derivatives within this box are computed. Just going from here, the derivative of the loss with respect to Z1. Can you give me the chain rule here? Just the high level rule. What's the chain rule? The two terms.
With respect to like all the U's.
So can you speak up, please?
With respect to like the U,
With respect to U, which U?
I guess all of them.
All U, okay. So dl over dz1 is going to be and
Multiplied by
du over dz, right? Okay. Everybody agree with this? The loss influences every one of the u's, right? And the z, I mean, every one of these u's influence the loss, and the z influences every one of the u's. So you must actually sum over the entire set. This is what we need, correct? Everyone with me? So, questions? No. So given that we have already agreed, okay, my handwriting is a chicken scrawl. What did I do there, Reza? How do these things disappear? I need to tie them to my waist with a belt or something. Okay. So let me write this cleanly, and then let's work our way out. So we agree that this holds, that the d loss over d z I equals summation over j, d loss over d uj, duj over dz. This we agree, correct? Okay. So what are the terms we must estimate over here? So I forgot your name again. I'm sorry, I can't read it. Okay, Mingwei. What are the terms we know over here, and what are the terms we must estimate when we are performing backpropagation? So I have two terms over here, right? So what are the terms I already know, and which terms must I estimate?
one we have already known.
The left is already known. This must be estimated. Right? Everybody with me? So let me draw this picture again. I'll draw this cleanly. Okay, as cleanly as I can draw it. This is the mini batch. Each one is influencing the corresponding U, right? Computing the corresponding U. But then each one is also influencing the mean, which influences these guys. And they also influence the variance. And then which influences these guys, right? So this figure makes sense to everybody, right? Now, if, okay. I can't see your name, really. You need to write with big fat pens, guys. So Nicole and Anushka, you are the next two guys, right? Question. For Nicole, so how many different kinds of derivatives do we have here? Will the derivative of u1 with respect to z1 have the same form as the derivative of u2 with respect to z1?
I don't think so.
You don't think so? Why?
Because like in the first case, the numbers are the same, but then the second one.
In the first case, there's a direct connection, right? So okay, fine. So now Anushka, now maybe you can help me here. What are the different ways in which u is dependent on z?
It's dependent through they. So I think it's like also the gamma and beta, and also.
So the gamma and beta are way down. They're already gone, right? So what are the different paths through which the u is dependent on z?
Like the direct connection, the mean, and the.
So this connection, then this connection, and this connection, right? You agree? And when I'm looking at this connection, I also have to consider every way in which z depends on sigma squared. Okay. So now, can you give me the derivative, a formula, general formula? How many parts will the derivative of u with respect to z have? You almost answered me, so maybe you can complete the answer.
I think one for each connection.
One for each connection. Lovely, right? So dl over du over dz, dui over dzi is going to be. Just tell me what the three things are. Partial u over partial z through this connection, correct?
Yeah.
That's one. What is the second one?
dui d mu b times d mu.
dui over d mu b times partial mu b over dzi, correct? And then what is the third one?
Same, but you replace the mu with the variance.
Everyone with me on this so far? Make sense? Right, okay. So now we just have to figure out what these individual terms are. Right? Easy. And so if I'm looking at this, d loss over du has already been computed. We need to compute these guys, the second term, which we must compute for every ij pair. And I'm just doing we're just going to work through this for only the direct connection. And the direct connection is, for dui over dzi, it has three parts, as we just saw. There's the first part, the partial ui over partial zi, if you assume mu and beta are constant. Then the second is partial u over partial mu times partial mu over partial z. So this is computed. These are all local derivatives. How much does u change if only mu is changed and not the rest? And the second is how much does mu change if only zi is changed and not the rest, right? And then the third one is this guy. So everyone, we all agree that these are the three terms, correct? So now what are the terms we must compute over here? There are 1, 2, 3, 4, 5 different terms we need to compute. With me? Okay, so you guys, Josh and Colton, you're going to be answering the next two. So I want to compute, so let me write this down here, up here, with so dui over dzi equals the partial ui over partial zi through the direct connection plus partial ui over partial mu b times partial mu b over partial zi through the mu connection plus partial ui over partial sigma b squared times partial sigma b squared over partial zi. That is the sigma connection. 1, 2, 3. Okay. So Josh, can you help me with just the first term? What would this guy be? Now, for this, I'm giving you all the formulae required. The formulae required to compute the mean of the mini batch, that's given on the slide. The formula for the variance is also given on the slide. And the formula for normalization is also given on the slide, right? I want you to tell me what partial u with respect to partial z is, assuming mean and variance are fixed. They're not modified. Yes, this is going to come from ui equals zi minus mean over square root of variance. I'm just ignoring the plus epsilon for convenience. And so from this, if these guys are fixed, this is the only term that remains. Implies the partial ui over partial zi is simply 1 over the square root of the variance. Everybody with me? Right? That's a very easy formula, right? And so let's look at this guy. And indeed, that's just 1 over square root of the variance. Lovely. And so I can go back to this formula. I've replaced the first term. This is taken care of. So Colton, what is the second term here that we have to look for? That's, can you speak up, please?
Yeah. dui over du.
So you need the partial of ui over mu b, assuming the variance and the zi are fixed, right? What is this? Again, look at the formula. This is simply going to be minus of 1 over square root of sigma squared from the formula, right? Everyone with me? Questions? No. Okay. So that's the derivative of the edge highlighted in blue up there, right? And from our formula, that just ends up being minus of 1 over square root of sigma squared. Now, Chetan, I'm going to skip you because you answered too many questions and asked too many questions. But so Cheng Han and what's your name? Tom. You guys are going to be answering the next one, right? So let me plug this in here. Now I need to compute this term. So this term has been computed. So Cheng Han, what is the next term to compute? Pardon me? So, but which term are we computing? Okay, so the next thing you want is this term, which is partial of mu b over partial of zi, and that is going to be 1 over b, right? That comes from the formula for the mean. Everybody with me so far? Nothing complicated, right? It's very easy. Once you actually begin working this thing out step by step, the complexity of the formula that simply vanishes. And so, lovely. That's 1 over b. So I've stuck in that guy, right? And then Tong, yours is, you're it for the next one. This has been computed as well, right? what is the next term that we're going to have to compute? So you want partial u over partial sigma squared, assuming assuming that mu and z are fixed, right? So what is that term going to be? Again, I remind you that the formula for u is u equals z minus mu over square root of sigma squared plus epsilon, right? So what is the derivative of u with respect to sigma squared? Does somebody else, Jay, do you want to do it? Come on, guys, this is easy. Okay, Katrina, I know you can do it.
Maybe like 1 over the square root of sigma squared plus epsilon.
Think of this. I can write this as, maybe I can help you, right? Z minus mu times sigma squared raised to minus half. Forget about the epsilon for now. If I write it this way, Tong, what is the derivative?
Minus 1.5
Times what? Sigma squared raised to minus 3 over 2, right? Why do you get confused if I just show it in the denominator? You shouldn't, right? Everybody with me? And so, voila, this thing is just minus z minus mu over 2 times sigma squared plus epsilon raised to minus 3 over 2. Easy, right? So, Jai and Sonhee, you guys are next. What is the next term to compute? I have already done this. So I've stuck this here, right? What is the next term to compute, Jay? Partial sigma squared over partial z, right? And so now, when I compute the derivative of sigma squared with respect to z, how many paths do I have from sigma squared to z? 2. This guy and this guy, right? So can you write me the formula for this? Just high level.
Partial of sigma squared over partial of zi
Partial of zi
plus partial of sigma squared over mu
partial mu
divided by partial mu to
partial mu over sigma zi. So everybody with me so far? This guy, right? So okay, Sonhee. Now I have to compute this formula. I'm trying to compute this formula, right? Now this formula has 2 terms. Pick one. What is this one? Okay, so let me actually pull that up. This one has 2 terms, as Jay just mentioned. I want the first term. Oh shit. Okay, you didn't see it. Did you see it?
no.
Okay, give me the answer.
2 times z minus mu over e.
Right? And so we have partial sigma squared over partial zi is simply 2 times z minus mu over b. Everybody with me? Straight up formula, right? Nothing fancy. So what is the next term to compute? Quentin? I'm not asking you to solve it. I'm just asking you what the term is.
So d sigma squared b e.
You want this term, right? Okay. So now this is a bit of a, it's a complicated looking formula when you actually work out the formula, but then if you just go back and look at the logic of it. Suppose we are speaking of partials, right? And so now a probability distribution has many characteristics. It has the mean, it has the variance, it has a whole lot of other things. And so if I have a probability distribution of this kind with this mean and this variance, and I change the mean to this is mu plus delta mu, and I don't change anything else, will the variance change? I'm only changing the mean, I'm not changing the variance, right? So what is the derivative? If I say if all I move is the mean independently of everything else, does the variance change? So what is the derivative of the variance with respect to the mean? 0, right? Think if, again, you have to go back to basic principles. What does a derivative mean? And if you go back to basic principles, the answer falls out, very straightforward. And so you can work out the arithmetic, it will come out to 0, right? And so this guy, the second term is 0. I don't even need to care about what mean over d mu over d zi is. The derivative of the variance with respect to zi is simply 2 times z minus mu over d. And so that has been plugged in. Crazy formula, right? But we just derived it. It didn't take very long. If I throw this at your face on a paper, you're probably going to get lost. But if you draw the figures down and then you work your way through it, it's 5 minutes work, tops. So everyone with me? And so this was the formula that you actually encountered in your homework. And if you didn't get it, you can work your way through it, and it's not so hard. So this is just the derivative of ui with respect to zi. I also need the derivative of uj with respect to zi. How does uj with respect to zi differ from ui? You don't have the direct line. So that first term is going to go away. This term will go away for the derivative of uj with respect to zi. I can just write the whole thing. It's just these guys. And without working out the arithmetic, I'm just going to give you the formula. But if you worked it out, you would find this to hold true. And the second term, if I equals j, this simply becomes zi minus mu b squared, right? So you will find that the overall derivative looks like this. For I equals j, you get that first term. For I not equal to j, you have only the first term missing. Observe that the second line is the same as the first line without the first term for I equals j. So this portion here, is basically the same. Just replace j with I, and you're going to get the first 2 terms here. The only thing missing is a direct connection. Right? Everybody with me? Okay. So easy. It looks very complicated, lots of ugly stuff, but then when you write it down, no big deal. And now, the complete derivative, I just have to sum over everything. And if I sum over everything, I just wrote out the formula, I plugged it in. And so the second term over here, this is summed over, again, this term gets summed, multiplied by d loss over duj and summed over all the u's. The third term gets multiplied over by d loss over du and gets summed over all the u's as well. The first term only applies to the direct line, so it has only one contribution. So simple formula. Now the formula is not very clear, but like I told you way back when, if you stare at any formula, it tells you a story, right? That's a nice thing with equations. And so this tells us a story about what the mini batch must be like. Okay, so here is my formula on top. And that's given me the derivative with respect to z, which I can keep back propagating. But then look at this. Suppose I have a mini batch where all the instances are the same. I have a mini batch of identical instances, right? Then what is, so let's take the first 2 terms, right? If I take the first 2 terms, I can write them as what's the first term? It is 1 over square root of, I'll skip the epsilon just for convenience. And the second term is minus times d loss over dui minus, and what was the second term? 1 over b times square root of sigma squared summation over j d loss over duj. Is that correct? So this I can group these things together and say this is 1 over square root of sigma squared times d loss over dui minus 1 over b summation j d loss over duj. I can write it like so, correct? Right? If all the instances in the mini batch are identical, what does this become? Infinity. Infinity? 0, right? The second term is the average of the last derivatives for the mini batch. But all the instances are identical. All the u's are identical, right? So this guy over here, this term, is simply going to be d loss over du. We'll use the common u for the entire mini batch because all the instances in the mini batch are the same. This will cancel this guy out. Josh. So
the variance between the batches be 0 though?
So within a mini batch, if I have a mini batch with no variance, right, then this second term is just, the first term is just the loss with respect to the u for that instance. The second term is the average of the derivatives of the loss with respect to all the u's. But if all the u's are identical, these two will be the same.
Yes. Okay.
Right? So this becomes 0. That makes sense? Okay. So the first term disappeared. And the second term disappeared. What about the third term? What will happen to the third term if all of the batches instances in my mini batch are identical?
Will be the same as B, so
The third term will also become 0, correct? Forget about the multiplicative term, multiplicative aspect of it. The third term is simply going to be, because all the dl over du's are identical, the third term is going to be whatever the constant times dl over du times summation over j z minus mu. And if the sum of the, and of course, that's just the difference between the average and the mean, that's going to be 0. So the entire term becomes 0. What does this tell us about how a mini batch must be composed? You seem lost, Josh. Did I lose you?
I get that the mean term goes to 0. I just don't get why the variance term.
It doesn't matter that the variance becomes irrelevant, right?
If they're all the same, isn't the variance between them 0?
Yeah, but I have a plus epsilon over there.
Okay.
So it's not going to blow up, right? So you have to be careful. So the plus epsilon is always there for stability, right? So that makes it 0. And so now, what does this tell us about the composition of a mini batch? If a mini batch is identical, all the instances in the mini batch are identical, what is the derivative of the loss with respect to zi? Can everybody say it aloud? Do you believe me? Right? And so what will be backpropagated from there on? There's no more information. We just got a bunch of zeros, right, for the entire mini batch. There is nothing else to backpropagate. And so we end up with a situation where you have a pole. Okay? Someone on Zoom, true or false?
True.
Okay. It's true, right? If all the instances are in the mini batch are identical or even very similar, the derivatives going past the mini batch, the batch normalization layer, are simply going to vanish. They're going to go to 0, and then after that, there's no more backpropagation. So what does this tell us about this nature of mini batches? They must be diverse, right? You want mini batches to have instances from every class and capture the diversity of the data. And this basically goes back to the very first principles. We want the variance in the mini batch to be comparable to the variance of the general data set itself, right? So the larger the variance of the mini batches, the more this thing will work. If your mini batches are all very consistent and all instances in it look identical, then you're not going to get very much out of batch normalization. So,
Prof, there's a question on Zoom.
yeah.
When is it advantageous to not use batch norm?
So batch norm is a general principle that it's, if you expect to have this kind of covariate shift, you want to use it. If your data have segregated structure of some kind, where you're likely to end up with situations such as these, batch norm will actually kill your ability to backpropagate errors, right? So yeah.
What happens if we choose mini batch size as 1?
You're not going to get any derivatives.
So if we use batch norm in that case, it would go.
You're not going to get any derivatives after that layer, right? Because dl over dz is going to become 0. Yes.
Why should we line the parameters twice, and if instead we could have just done batch norm even before we did the initial function?
So the point is this: you can do it. Okay, you can do the batch norm at any location, but even after batch norm, you're going to be finding differences between your mini batches. And because your network is such a nonlinear function, as the data pass through the network, the mini batches are going to move around, and then you're going to find yourself in exactly the same situation again, which is why we apply batch norms so many times through the network, right? Simply because the nonlinearity of the network is going to move things which are very close far apart, right? Okay. So now here's another thing. You're speaking of mini batches and you're normalizing with respect to the mean and the variance of the mini batch, but this only applies during training, right? During inference, you have to perform the same processing, but where do the mu and the sigma come from? If you're performing inference on a single instance, there is no mu, there's no sigma. So now we need to guess mu and sigma. So what we typically do is, once your training is entirely done, you pass your entire training data again in mini batches through the model, and then you compute the means of all of the mini batches, and the average of the means of the mini batches is going to give you the inference time mean. Similarly, the average of the variances of the mini batches, scaled up just a little bit by b over b minus 1 to make it unbiased, is going to give you the variance that you will use during for batch normalization during inference. That's because you need the mu and sigma squared. And so you're estimating them by passing all the mini batches of the training data through the model and computing their means and variances and taking their average. And of course, so batch norm can be applied to some layers, selected layers in the network can be applied in any odd way. But you would apply it at any location where you expect to see this kind of covariate shift, contingent on the expectation that all the mini batches have diversity, because if they don't, then this thing is going to kill you rather than doing anything useful, right? But here was the first paper on batch norm by EF and Zegedi, and you can see how without batch norm on this particular model, it takes 30 million iterations to converge or something, and with batch norm, it converges in a fraction of the time to a much better result, because the derivatives, you're normalizing things and derivatives are much better propagated. So this has become a staple, right? So our lesson from this is covariate shift between training and test may cause problems and may be handled by batch norm. I have 3 minutes, so I'm going to try to get through one more topic. So there's one more caveat to worry about. When we train the network, we end up trying to train it from just a few samples of this kind. And so we are just trying to train the error network to minimize the error at our training samples, but there's nothing stopping the network from learning something of this kind, where it minimizes the error at your training points and doesn't do anything useful at other places. It still continues, it's still smooth, but nothing like the function that you were trying to estimate, right? So, what can we do to sort of try to prevent this sort of behavior? We need additional smoothing constraints that will fill in the missing regions acceptably, right? And for this, let's go back and look at our one-dimensional example to get an idea of how this might be achieved. Now, here is my 1D example again. I have data of just one variable, and it's a binary classification problem, 0 or 1. If I were just training a network, I would expect it to compute the posterior probabilities. So the blue curve is what you really want it to compute, right? But remember that the network is a universal approximator. It could pretty well go ahead and compute this function. Would you want this? Yes or no? No, right? So, but then, why is it able to compute this function? It's able to compute this function because the perceptrons in the network are individually able to capture very fast changes. So I'm going to assume a sigmoid activation, but this would apply to pretty much any activation, right? I can learn this function, I can model this crazy function if all of my perceptrons have threshold activations. Then I can jump up and down, suddenly and get this kind of crazy behavior. And if my network is of the kind where I can actually, if I had some learning mechanism which could allow me to learn a threshold activations of the right position, it would end up learning this. And this is not what we want, right? But then consider a sigmoid activation. A sigmoid activation has this property. It's 1 over 1 plus e raised to minus wx, right? And it's going to look like this. For w equal to 0, what's it going to be? It's just going to be a constant, right? As w increases, this sigmoid is going to get steeper and steeper and steeper. At w equals infinity, this is going to be a threshold. That's just the property of the sigmoid. The magnitude of the w tells you how fast it can rise. And so now, if I allow my w to be unconstrained, then my function can learn this guy. Because every edge can be arbitrarily steep. It can follow the latest error, and everybody's happy, right? I want to force the function to not learn those things, which means I want to say the w's must not be large enough for the function to raise very steep, right? How can I do that? Anyone? Jimin, how would I do it? Question? How would I do it? I want to impose a constraint on the weights, correct? I want to say that the perceptron must not rise too fast. So what I really will do is to say I'm going to add an extra constraint on w that forces it to be low. So not only do I want to learn my function, I want simultaneously also want my weights to be small. And so the way I will do it, here's your standard loss function, right? Instead, I'm going to, is there a question? Yeah.
If you constrain the weights themselves in prior layers, won't that affect the future layers as well, like propagating through the network?
It's going to affect everything, but the point is if you have even one layer where the past changes are allowable, then you could end up learning this crazy function, right? And so you want, instead of just using your standard training objective of minimizing the average divergence, I want to say minimize the divergence while also keeping the weight small, which is to say I'm going to add this extra term, which is simply the sum of the squares of all of the weights weighted by some lambda, and I say this must also be minimized. And so when you say this must also be minimized, then you're literally saying minimize my loss while also keeping my weight small. And that will give you smoother functions. And of course, how important it is to minimize the weights is controlled by lambda, right? And so when I work out the arithmetic, the derivative of half lambda summation w squared is simply going to be lambda w. So the new derivative is going to be your standard average divergence plus lambda times w, right? And so when I correct w by saying w minus this new derivative, I'm going to get the old divergence, but then I'm also going to be subtracting lambda times w, so you end up with a factor that shrinks your w before you correct your, add your gradient step, right? We called it something in the homework. What did we call it? Not just regularization. There was a weight, we call it weight shrinking or something of that kind, right? Weight decay. You are multiplying the weight by a small number, a number less than 1, to reduce it, which is basically telling you the importance of keeping the w small, right? And so this simple business of shrinking the weights before you add the gradient is nothing more than applying a regularization term that ensures that your weights are also reduced along with your parameter updates. So that's over here, okay? So anyway, I'll stop here and we'll meet again at 8 o'clock on Zoom. I went slower than I could. I expected to stop earlier. Thank you, guys.